This is lesson 44 of the Quantum Mechanics mini lecture series, part 3 of the simple quantum system case. So as mentioned in a previous video, an electron, before you measure it, can be spinning in both the spin up and spin down states at the same time. Okay, so this is prior to measurement. Okay, before you make a measurement, before you get any numbers out, the electron exists in this sort of hazy state, mix of states, I should say. And it turns out that on average, okay, upon doing experiments, you find that the electron is in the spin up state, I should say the spin down state, 50% of the time, and in the spin up state, 50% of the time, on average. Okay, and as such, here's how we should be writing this technically speaking, okay, in using quantum language. I'll explain what this means. Just a sec. So I've put a 1 over the square root of 2 factor out the front. You might be wondering why this is the case. Well, this is because it'll actually determine the probability of finding the electron either the spin up or spin down state. Okay, it just makes the maths work. And this mathematical expression tells us what's known as the wave function. This thing here. Wave function of the electron. Okay, here's how we write it. The wave function is given the symbol capital psi, typically Greek symbol psi. And we set that equal to this thing here. Okay, and the wave function it's basically a mathematical statement which describes the quantum state of the electron, or for any other quantum object for that matter. Okay, it's like a tag, if you wish, that goes along with the electron. So to get the probability of the electron being in the spin down or spin up states, you need to actually take the square of the wave function. Here's what I mean. So to find the probability of the electron in the spin down state, as follows, we simply take the square of its coefficient, okay, in addition to taking its absolute value. Let me show you what I mean. So probability, PR, probability, finding the electron in the spin down state is given by this. And technically speaking, the psi should have a bracket, a ket as well to go with it. Okay, because it's describing a quantum system. Okay, here's what you need to do. Okay, absolute value means you're going to take the positive. Okay, it's basically a measure of how far you are from the from zero. That's what absolute value is. If you have minus 10, absolute value is just 10. Okay, it means it's 10 units away. Minus 10 is 10 units away from zero. Okay, on a number line, if you think of it, minus, let's say, 1,000. Okay, absolute value is 1,000. So you're really getting rid of the minus there, right? And square, that just means take the thing and multiply by itself. So the coefficient of the spin down state is just 1 on root 2, because if you expand this, okay, you will get this. The coefficient, the number in front of the spin down state, is 1 on root 2. So it's the absolute value, 1 on root 2 squared. Okay, if you punch that into a calculator even, you'll get this, 0.50. That's 50% or a half. Okay, so there you go, the maths works that way. 50% chance of finding the electron in the spin down state. Okay, and similarly, you can do the same thing. I'll leave that as an exercise for you, to find the probability of the electron being in the spin up state. Okay, and so therefore the probabilities, when you add them up, you'll find that they add up to 1 indeed. Okay, 100%. Probabilities can always add up, must always add up to 100%, right? And you would have noticed that I've written it in a way such that the wave function, so I've used absolute value as well, in case you get complex numbers, okay? So instead of writing this, I've got this because of complex numbers, right? Complex numbers, you've got square root of -1. When you take the square of that, you get out real numbers, okay, like -1, or I should say 1, right? Measurable, actual real numbers, not imaginary numbers. So that's why the absolute value is there too. And the absolute value is also called the modulus, right? This notation is called modulus. And in the next video, I'll generalize this expression here for any quantum system.